All right, the final video in this knapsack problem series. And we're going to look at basically this diagram and we'll step through some changes in the code to arrive at our final form. So you noticed from the last video that we were populating this array, right? Step by step. Now this optimization lets us know that we actually don't need every single row. Well, firstly, we only need like maybe the current row that we're filling and the row right before, because that's what determines what the next row ends up being. And there's some text here to that effect that we can read. So can we do even better? Now, did the text really do it for me? I can't really say, to be honest. But what it is the code though made things a bit clearer to me. And it's a thing where we hold on, give me a second. Okay. All right. We have this temp variable, right, that holds on to the previous row. And then we loop through every single item here, every single item in our item array. And when we're done, when we're done with this inner loop, every single time we're done with this inner loop, we update splice. We update DP. So just bear with me. All right. Let's use this diagram, okay? Because I have the code set up already, and what I'm gonna do is you can take a good look at the code. So this is what it looks like, right? This next optimization that we're making, and we're making that optimization because we actually don't need this whole 2x2 array that we used in the last video, right? And I can show the code from the last video here. Okay, we don't need this 2x2 array, right? This a space optimization. We don't need this. Instead, what we want to do is work with just two one-dimensional arrays, okay? And so we cut down the space significantly. We're only dealing with two one-dimensional arrays, okay? And now what happens is one array is being overwritten over and over again. And I'm saying a lot without saying a lot. So let me just step through this with a debugger, okay? So now, all right, I set it up. Just pay attention to what's going on with every redo. I want you to look at this temp variable, all right? So with every iteration, where we end up actually filling it up just like before, just like in the previous video, with ones, right? The first time. And then it comes over here and then it's spliced onto the to DP. So DP then holds all those values, right? It's copied on there. And then we move on to I being 2. So it starts from 1, then it goes to 2. So what just happened was this row, this whole process of this row being filled. That's literally what just happened. And we didn't need to fill this. We didn't need a 6x6 or 4x6 array. We only needed two one-dimensional arrays, right, of length 6. That's all we needed. Okay. And in this case, we just keep going and just keep observing, right? Keep observing what's happening with temp, because temp is what's being changed. So you notice that switch over to 5 down here, similar to this 5 that comes in there, and so on, and then 6, and then every other thing remains 6. And then lastly, we're done with that. We copy it onto DP, and DP changes into this final form here. Look at that. So that's the optimization. That's what we're running with. So instead of using 2 arrays, we're using 1. Lastly, I want us to look at, and this code is available right in the description. You can find it on GitHub. I want us to look at the final boss of this fight. I don't know why it's crying. Oh, of course. It's a VS Code quirk where you're using TypeScript and you have the same variable open in multiple windows. Same called named function in multiple windows. It errors out like that. But let's walk through this one with the debugger as well. So use this debugger. Now this one is a bit different in the sense we are looping backwards, okay? And they give an explanation, like a verbose explanation here. They say, oh, can we do even better? Because we're obsessed with doing everything even better. Now we're trying to move from 2 6-length arrays to just one array. And they give a whole explanation here. But I think, personally, I find like walking through the code just does it for me more than like reading all this stuff, really. So what they end up doing is they're skipping the else statement. So if it doesn't fit in the weight, we just don't do anything. We're not even checking if it fits in the weight or not. We're always just updating DP index at J to the maximum of whether we take it with it or whether we take it without it. Okay, and somehow, and that works, right? That actually works. So because in this case we're using one array for everything, unlike in this case where we had this else, where we're copying a second array onto the first, here this operation essentially evolves to this temp. You're copying it into itself, which is basically doing nothing. And so when we're computing it, we don't need to do this, right? Because we're trying to use one array. We don't need to do this. And all of this is just to skip that last copying step. It's just to get rid of this, right? Mainly because this is an expensive operation. So we want to skip that. That's why we get rid of the else. Notice the else statement's gone. This else statement's gone completely. We're only using one variable, DP, and updating it at various capacities, right? And at the end of the day, we loop backwards, actually, from the highest capacity to when J is bigger than, so as long as J is bigger than the current weight, because if the weight is bigger, we can break out of the loop, right? If that weight won't fit at that capacity, there's no point in evaluating it. Just skip that step. And so we wind up with what we have here. And we can step through the code to just to see between the code and the diagram. So for the first case, right, you notice that there's a 1 here, right, in DP, right? Because we're evaluating a J of 5. So at capacity of 5 with the first item, right? That has a value of 1 and a weight of 1. So maximum value you can have at that first instance is 1, no matter the capacity, because we are only evaluating this first item. Oh, my face is blocking it. Oh, thank God I saw that. Let me move this up a bit. Okay, wonderful. So we're just evaluating, and you can see that it matches perfectly, right? This algorithm still reproduces this diagram for us, just row by row. Okay, still reproduce this thing for us, right? As you can see here. And now we're evaluating the second item, yeah? And it looks like this, right? This algorithm, similar looking algorithm, will start to populate things just like it did in the prior diagram, okay? Just like it did here, right? And I skipped one step and started evaluating the third one already. Like you see, I is 2. So it's the index at 2. It's gonna start with, it's gonna end up with 10 here and 9, 6, 6, like the same thing. Just observe. Okay? Then it breaks out of it. It just keeps going. Okay? So, yeah, it's gonna give us 10, and we're done. Like we barely had to loop. We had to loop very few times to get this out. And that's the final optimization, the final boss, if you will, for the knapsack problem, right? This was a doozy, right? This was not convenient at all to make. But let's look at the solution summary. Well, not the solution summary, the time complexity. So it's O of n by c, where n is the number of items, c is the total capacity of the knapsack. Okay, that sounds about right. And the outer loop runs in O of n time. And the worst case, where all of our items have a weight of 1, the inner loop runs at O of c time. That's the explanation. And then the space complexity is O of c, which is the space required by the DP array for this final form, right? It needs O of c. And that's all there is to this terrible, terrible classic problem. See you around.